Hey everyone, welcome back to the channel. So the problem that we are going to discuss today is minimum spanning tree. So basically this question has been given to you in greedy, okay, which it shouldn't have been because it's a graph problem, but we will discuss, okay, no worries. So what we have to do in this question, let's understand. Before that, I'll just quickly check if we are live yet. Okay, so you are given a weighted undirected graph. So what I am assuming is, in order to understand today's lecture, you need to have some basic understanding of graphs and all. Only then you will be able to understand. And if at this moment you don't have, then when we will be going on graph topic, then you can come back and solve this question, right, and have a look at this. So let's discuss it. So what is given to you, that this is a weighted undirected graph, okay. Your task is to find the sum of weights of the edges of the minimum spanning tree. So for that, first let's understand what is the minimum spanning tree. So for example, if I take any example, like I'll just draw a tree for you. Let's understand what is the minimum spanning tree. So basically you are given a graph. For example, if I have a graph like this, it's an undirected weighted graph, right? 2, 3, 4. Okay, for example, I have something like this, and there are some weights associated with it. For example, this is 2, this is 2, 3, and 1, 1, 2, 4, right? For example, this is, so MST is what, that you have to connect all the vertices in such a way that the weight of the edges is minimum. The sum of all the weight of the edges that are connecting to those vertices is minimum. For example, from 0 you have 2, 1 and 3. Okay, I am connecting to both of them right now. What is the weight? 2 plus 3, 5. Total weight is 5 as of now, what I have. Okay, from 1 you can go to 2 via this node, and to 3 you can go via this node, and let's say this also has some weight of 1. So right now I do not have any other option but to choose it. Okay, but let's say I can get connected to 3 from 1 also and from 0 also. I'll choose the minimum one. Okay, 1, this is 1, this is 2, this is 3. As of now, let's say this is what I have. Okay, fine. Next up, what I have is, this is for example 2. Okay, I connect to 2 using this 1. If I connect to 2 from 3, that also is 1. So the edge is anyway going to be weight is going to be 1. I can choose either of them. Now I have 4. Should I connect to 4 via 3 or via 2? If I connect via 2, I'll have some minimum of these two is 2. So I'll connect to 4 via this weight. So basically now I have all the vertices and the edges in such a way that the sum of them will be minimum. That's what I have chosen. Might not be there might be some error in, because I just created this test case for you to understand. Okay, so if I understand it in this way, what I have in the question is, you have 0, 1 and 2, correct? The output is 4. How they have chosen this 4? Understand, you have 3 vertices. I am connected to 3 vertices, but see, you can go to 2 from 0 via 1. Okay, it chose this one. From 2 you can go to 1 via 3, and you can go to 1 from 0 via 5. So what they did, I just have to connect one edge. Okay, I want to reach to my vertex using one of the edges, the one which will be minimum. It's better to choose that because I want minimum spanning tree. So the sum of the edges I have now is 3 plus 1, 4. Got it? So the intent, what you'll eventually see, that the number of edges finally what you have will be equal to number of vertices minus 1. That's, and these v minus 1 edges, the sum of them should be minimum. That's how you have to basically traverse over your graph. And this what we get right now with the minimum sum of weights is known as MST, minimum spanning tree. Got it? So if you see how many vertices we had, 1, 2, 3, 4, 5. Now how many edges we have? 1, 2, 3, 4, 5. We can, no, 1, 2, 3, 4. This is 1. I counted this as an edge. Okay, so we got 4 edges. That's the minimum spanning tree in short, what I could, in very short, what I explained. Okay, so this is the intent, that you need to have some prior knowledge on graphs, what is a MST, so this question will become easier for you. Now the things that we just discussed, now we need to understand how, using some what we can do, what concept we can use here to get the minimum spanning tree. So when we see this, okay, we first of all we need to traverse over this graph. So we need to have an array which will keep the track of what all nodes I have already visited. For example, let's say I take a visited one, I want to traverse, and I also want to keep a track of what all nodes I visited, and I am going to traverse over this graph in such a way that the one with the minimum weight is chosen, right? So one thing, let's say it's a, actually I'll just name it pair, although I'll have three things in pair, class pair. I'll take a class pair which will actually have three parameters. Okay, so what are those three objects? I am going to have the parent, weight, and the node itself. Okay, it can be in any order. For what I have chosen here is, let's say for example we have taken a class pair in which we are taking weight, node, and parent. Why we are taking it, I'll tell you. First let's understand one by one what are we going to do. Weight, one second. So this pair, actually it's a triplet, I am repeating again, this is just for the namesake. What I am going to do here, basically we are going to have a class pair which is going to keep track of what is the weight associated with that vertex. For example, if I am going to 1 from 0, then I should be knowing that if I am going to 1 from 0, what is the weight? So the weight associated is 2. The node from which the node at which I am going, this is going to be treated as your node here, which I am taking. So node is 1, and the parent from where I am reaching to 1 is going to be this node 0. Got it? Okay. Now when I have this information, from using this information I am going to declare a priority queue. So you can use a comparator method on weight such that this priority queue, so what it will do, it will make sure that whatever node I have, or this pair object I have in my priority queue, it should be on the basis of weight. Use comparator method. I'll use comparator on weight. Why so? So the intent here is that as and when I am traversing over any node, if let's say I go over 0, I insert into my visited one, okay, and in my priority queue I insert all the edges all the neighbors. So for example, this is your priority queue, okay, fine. So all the neighbors that are associated with 0 I will insert into this priority queue. Now priority queue will make sure, since I am using my comparator method on weight, this is the weight, it will make sure out of all the neighbors. So right now what are the neighbors of 0? 1 and 3. So it will make sure the one having lesser weight will be at the top of my priority queue. That's how priority queues are, right? If it's a min heap kind of a priority queue, which it is going to be, that will make sure that on the one having the lesser weight will be at the top of my priority queue. So ideally this will contain a pair object which will have weight which is the minimum one, 2 is the minimum one. Then other information that it will have will be your node at which you are reaching and the parent from where you are reaching. Got it? And the other neighborhood will be 3. So it will come after this. The weight will be 3, your node will be 3, and parent will be 0. So that's how you're going to install information in your priority queue. So what next you will do? So 0 has been visited. Now you remove the top of the priority queue. When you remove it, you see that it has not been visited. So you insert this. This is the node that you are visiting. You insert it into your visited list of arrays. When you remove it, you make sure that you insert. Now you are traversing its neighborhood. So what are its neighborhood? 1 is connected to 2, 1 is connected to 3, and 1 is connected to 0. We'll see 0 is already visited, so there is no point of inserting 0 in priority queue. The nodes that are left to be inserted are 2 and 3. So now priority queue will decide the one having lesser weight will be inserted as before the other one. So that out of 2 and 3, the one having the minimum weight, it's 1, both are of equal weight, so both will be inserted, means any one of them we can pick up. Now out of all the nodes that I have here, I'll have weight 1, node 2, and parent 1. Other one what I have is node weight 1, node 3 and parent 1. Now out of these 3 objects, the one having minimum weight will be in the front of, will be at the top of my priority queue. That will be taken care by the priority queue. You don't have to worry. This is just for the representation purpose. Okay, so now the other one that I'll be basically, when I'll remove, not, this is not the pair that is going to get removed, the one having the minimum weight. It can be either this, it can be either this, because both the weights are same. So this is just for representation purpose. Don't get confused that it is coming later in your priority queue. This is the one that will be in the top, at the top of my priority queue, right? So once this is removed, I'll insert this into my visited array, and I will insert its neighbors. 1 is already visited, 3 is already visited, right? 3 is already visited, and 4 is left. 4 will be inserted. Okay, so there is no other option left. 4 will be inserted, and the weight associated with it is 2. So this 4 and parent is 2, right? That's how we are inserting. Now the which is the minimum weight of also 1 is left, 2 is left, and 3. This is the next node that I'll be removing from my priority queue, and I'll try to insert its neighbor, but we will see that has been already visited. I am already visited 0, 2 and 4. So now you just one by one remove from the priority queue, and the sum that you will get. So basically here I have just shown the node, but you will be inserting pair only. So the weights associated with them in the order in which we have just removed, that will be the total sum that you are going to return, right? So this is all about it. Let's go to the code, have a look, and then we'll probably do one try run and you'll understand it properly. I'll just meanwhile check. If you guys have any doubts, you can ask me. Should I increase the font size? Wait, I think the font should be better now. Okay, let me check if it's reflecting yet. Yes, it is. Okay, so let's have a look what we have done here. For example, if I talk about this 0, 1 and 2, quickly we will have a look. I'll just show it to you on this 0, 1, 2 itself. First test case itself I am taking. Zero, 1, 2, and what are the weights associated with them? 5, 1, 3. Okay, fine. So this is your graph. What have we done? We'll just do a quick dry run so that you guys can understand. This is the priority queue that we have declared here. Okay, and this is the comparator. We have used the simple lambda function here. You can use, if you, whatever way you are comfortable, use that. This is the lambda function we have used. You can use comparator method. Pair class is what we have already defined, as I have shown you above. Okay, so based on that only we have used these terms like the .wt and all. I'll just show you also. This is what we have used as the terms. Okay, fine. This is the constructor in which we have initialized them. Okay, so into your queue you are starting with the 0, 0, minus 1, which reflects what? First thing what you are inserting is weight, other one is your node, and the third parameter is your parent. Please understand, you are inserting a new pair into, this is your priority queue. For example, let me draw it this way. This is your priority queue. So you have inserted 0, 0, minus 1 in the beginning, right? This is your adjacency list. Since the graph that is being given to you is of the form of a 2D array, right? So in this 2D array, they have given you your node, the next node that it is connected to, and its weights, right? So it will have 3 columns. If you see in your array, it will have 3 columns: the node it is connected to, and the weight associated with it. So I've just converted it into an adjacency list, that is an array list of array list. So this is something you should be knowing, and even if not, once you are doing your graph portion, you'll get this thing very clear. You don't have to worry about it. Okay, just simply converted it into an adjacency list for the ease of accessing the nodes. Okay, now this is nothing but we are just converted this into an adjacency list. What we are doing, we are just picking up the nodes from your array and converting it into a list. This is I2. I2 represents what? I think it represents your weight, right? Because in your pair class we are inserting weight first, then I1, basically I belongs to those edges. So I right now, for example, if this is your I right now, so this part I of 0, 1, 2, I of 2 will represent weight. In your pair I want to insert weight, so I'll represent it with I2. I want to insert the node, so I will insert it using I1, and if I want to represent the parent, I will insert it using I0. So that is what we have done. Okay, in case you are wondering what we have done here. And the other one is just we have changed the weight is as it is. What we have changed here, the weight has been inserted, the parent and the node. If 0 is connected to 1, 1 is also connected to 0, right? So in my adjacency list, I am inserting list in such a way I have weight. If I am connecting from 0 to 1, what is the weight, then the node which it is connecting to, and what is the parent. That's how I am adding into my this adjacency list. Okay, then same goes for 1. So I'll see that 1 is the node, what is the weight associated with 1 if 1 is connecting to 2. So that's how we are creating it. Now coming on to this boolean visited array. Now simple thing, like we used to do in trees, we used to do level order traversal, right? The only difference is here it's a priority queue based on weights. It will make sure that the one with the minimum weight will be the top of a priority queue. Okay, so while your queue is not empty, you will take the first pair, that is queue dot poll. So I'll get the one in the top of my priority queue. I'll check if it has already been visited. I'll check visited of p dot node. If this is already present in my visited array, this is your visited array I just showed you above. If visited already contains this, you don't do anything, right? Means you just go ahead and do the next iteration. If not, then you insert it into a visited array, mark it true, and then you have to add to your final weight. We have to return the sum of all the edges such that it's a minimum spanning tree. So you have to add that weight to your final answer. And then you are visiting with this loop, you are visiting the edges of, you are visiting the neighbors of the node that you have just removed from your priority queue. And I told you the way we have to insert it. If it already has been visited, do nothing, otherwise add it to your priority queue, and priority queue will take care, the one having minimum weight will always be in the front of my queue. So that is all about this question. Okay, so I hope you have understood this, and yeah, so that's all. You can use this code if you want to. Okay, so if there are no doubts, I'll just wrap it up. Okay, fine then, that's all. This is your class pair. Don't forget to define it, because we have kind of customized this in our way so that we can use this lambda function as a comparator over my priority queue, and converted this edges into adjacency list. This is the other extra task we are doing, and then exactly what we discussed in the explanation, that's what we are doing. Fine. So okay then, see you all in the next lecture. That was all for today. Fine. Thank you everyone. Bye bye and take care.